This is the first in a series of videos about acid and base strength. In the last video, we talked about how acidic or how basic a solution is, and that depends on how strong or weak your particular acid or base is in the solution. So we're going to talk about what those look like and how they're different. So the first and easiest one to talk about are the strong ones. So we'll start there. So strong acids and bases are strong electrolytes. Remember from a couple videos ago, strong electrolytes completely separate into ions in solution, and so too do strong acids and bases. They fully dissociate into ions in water. Okay? And there are not that many strong acids and there are not that many strong bases. So here is a table. I'll give you a second to take a screenshot of that for your notes. Okay, play when you're ready. So on the left side, we've got 6 strong acids. And you can see all of them have been written so that there's a proton on the left side because acids donate protons. So this style of writing emphasizes the proton that's going to be donated. And we can also take a closer look at what these are made out of. We can see we've got chlorine, bromine, and iodine in these. So these contain elements of group 17, which are nonmetals. So many of these strong acids are a hydrogen and a group 17. And then over here, both this compound, HClO4, and these two, they all have oxygen. Most of them several oxygens, and these are called oxyacids. So we've got halogen strong acids and oxyacid strong acids, and those are the two types. And you will want to memorize these, both their structure and their names: perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. And then over here, we've got the 6 strong bases, and we can see that all of these have a hydroxide in them. So they would all satisfy both the traditional Arrhenius definition about hydroxide and the more useful Bronsted-Lowry definition about donating or accepting a proton. So all of these are going to accept a proton. And if we look a little bit more closely at what they're made out of, we can see that these first 3, lithium, sodium, and potassium, they are from group 1, and they are all metals, metal hydroxides. And down here, these 3 are from group 2, and they're also metals. So all of the strong bases are made up of group 1 or 2 metal hydroxides. And you'll want to memorize these as well. These are called lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. If you're not into memorizing, the other way to recognize these as strong acids or strong bases is that they are usually not listed in a table of equilibrium constant values because their equilibrium constants are so strong that they don't include them in the table. All right, let us return to the notebook paper. So now that we know what the strong acids and strong bases are, let's look at how an equilibrium ice table might look like and look at how the strong acid dissociates in solution. So we're going to make an ice table in molarity. And whenever we make an ice table of an acid in solution, we are always going to use the acid ionization equation. I'm telling you, this bad boy is important. So acid ionization looks like acid, which is aqueous, plus water, liquid, goes to base plus hydronium. And I want to specify what I mean here. So I've written HA. This is a generic form for an acid. So I didn't leave myself a lot of space here, but this is a generic acid. And then A minus, that's the HA minus the proton. That's going to be our generic base. Because sometimes there's just too many letters in the name of the acid base or in the formula, and we just don't want to write the whole thing. So we just cheat and write it as HA and A minus. And I also want to draw your attention to the arrow. Note how this is a one-directional arrow pointing towards the products. That's because a strong acid or a base fully dissociates. So it only goes in the forward direction. Okay, so there's our ice table. Add in a few lines here. Okay, so the information we have from the prompt is that we have 0.5 molarity of a strong acid. So that's our initial concentration. So we can plug that in here in the initial row for HA. Water is a liquid, so it's the solvent. So we'll put a squiggly line in that column because we won't include it in our K expression. And we don't have any of the conjugate base present initially. And for H3O plus, we're going to put approximately 0. This is because technically, whenever you have water, you have 1 times 10 to the negative 7th H3O plus in the solution from water. That number is so small that we usually don't have to worry about it. So we'll write approximately 0 to indicate that we're ignoring that small number. Okay, whenever we make an ice table, we always calculate the shift to figure out which direction the C line is going. And we don't even have to do the math because we have 0 on the product side. 0 means that Q is going to be less than K, and we're going to shift to the right. Don't even have to do the math. So shift right means we lose reactants, we add products, and then according to our stoichiometric numbers, the amount is going to be the same, 1 and 1 and 1. And in this case, here's the kicker, because this fully dissociates, all of the strong acid is going to be used up to produce conjugate base and H3O plus. So once we reach equilibrium, all of the molecules of HA are going to be gone, and we're going to have an equal concentration of A minus and H3O plus. And this is just like what we said before, where we said the K expression was about ions over molecules. For a strong piece that fully dissociates, everything is here turning into an ion and nothing is here in the molecule. So we have a large number over a small number. So all of our molecules go to 0 and our H3O plus ions all go to their maximum value. So this is an important difference to understand. Okay, acid. Now let's do base. Let's say we have a 0.5 molar solution of a strong base. I'm gonna leave myself a little bit more space here. That was a pretty squished table up there. So ice table. And this time we have a base. And whenever we do an ice table for a base, we are going to use the base ionization reaction. Another good one to remember. And we're going to write it in generic terms just like we did up here. So generic base, aqueous, plus water as a liquid, goes all the way to generic acid, aqueous, and hydroxide, aqueous. And now that I think about it, I'm going to go back to the last one and I'm going to indicate strong over my generic acid, and I'm going to write strong here in the second one over my generic base. Because traditionally, we don't even bother writing an ice table for a strong piece because it looks kind of silly. It looks like the one we just drew, or one of the numbers goes all the way to 0. but I think drawing it is a good way to understand how a strong acid and a strong base are different from the weak counterparts. Okay, so similar situation down here. We've got 0.5 molarity of a strong base. That's our initial amount before any sort of a shift has happened. So we'll put 0.5 there under the generic base. We'll put a squiggle under water because we don't include that. We have 0 of the conjugate acid initially, and we have approximately 0 of the hydroxide initially. Remember, because there's 1 times 10 to the negative 7th present from water, which is probably too small to count. Okay, when we do our change, we have to figure out which way Q goes. And again, there's a 0 on the product side, so we're going to shift to the right. So we're going to lose reactants and add products. And then because this is a strong piece and we fully dissociate, all of the base is going to be used up and it's going to go to 0. And it's all going to convert to the other side to make conjugate acid and hydroxide. So we're going to end up with the full concentration that we had of the strong acid becomes the concentration of H3O plus at equilibrium. That is a wet erase marker. And the full concentration of the strong base at equilibrium becomes the concentration of hydroxide at equilibrium. So I hope you see where I'm going with this. We can just take the concentration of a strong acid and immediately assume that it's equal to the concentration of hydronium. And for a base, we can assume that concentration is automatically equal to the concentration of hydroxide because it's approximately 100% dissociation into ions. And that's why we call them strong. So in the next video, we will talk about weak acids and bases and how those ice tables look a little bit different.